The next time you look at the moon through the window, remember this. You are seeing the remnants of a planetary traffic accident. 4.5 billion years ago, Earth had a sister named Theia that crossed our path at 15,000 kilometers per hour. The impact was so violent that it instantly vaporized the Earth's atmosphere and left us spinning so fast that a day lasted only 4 hours. Today we are going to reconstruct the exact moment when our planet became liquid, when molten rock rained down for centuries, and from the ashes of that destruction, the light that illuminates your nights was born. About 4.5 billion years ago, the solar system was a chaotic and violent scene, very different from the order we know today. Instead of the well-defined planets peacefully orbiting the sun, there existed a vast disk of gas and dust, remnants of the molecular cloud that gave rise to our star. How does a collection of particles floating in the void transform into a system filled with worlds? The answer lies in gravity, that invisible force that gradually gathered matter to form the first planetary embryos. During this period, known as the era of accretion, millions of rocky and icy fragments constantly collided with each other. Some of these collisions destroyed smaller bodies, but others allowed them to merge, giving rise to increasingly larger objects called planetesimals. Have you ever wondered what it would be like to experience an endless meteor shower? That was the day-to-day reality in the primitive solar system. Constant impacts, mergers, and destructions. A true cosmic laboratory where only the largest survived. In this hostile environment, planet formation was a slow and random process. As matter accumulated, some cores grew large enough to begin clearing their orbits, attracting and absorbing their smaller neighbors. Thus, protoplanets emerged, massive bodies that did not yet have the stability or final shape that planets present today. But what happened to the bodies that failed to become planets? Many of them ended up as asteroids, comets, or were permanently ejected from the solar system. The most fascinating aspect of this cosmic chapter is that chaos was the norm. Young planets were not alone. They shared space with other protoplanets, some nearly as large as Earth itself. Orbits were unstable, and collisions were inevitable. In such an unpredictable context, any close encounter could change the fate of these worlds in gestation. Asking how likely it was for two protoplanets to meet was not just a matter of chance. It was a fundamental part of the process that shaped our home, and as we will see, it was precisely this tumultuous environment that allowed the moon to emerge as we know it.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
What exactly was Theia? To answer this question, we first need to imagine the chaos of the primitive solar system, filled with wandering bodies in formation and frequent collisions. Theia was not just a simple space rock, it was a protoplanet, meaning it was a sizable object, much larger than most of the asteroids we know today. According to scientific estimates, Theia was about the size of Mars. This means it had enough mass to exert significant gravity and attract materials around it, consolidating into a rocky sphere in the process of growth. But where did Theia come from? Planetary formation models suggest that Theia formed in the same region of the solar system where Earth was born, about 4.5 billion years ago. Back then, the region was like a congested highway of planetesimals and protoplanets, all competing for matter and space. Theia likely shared an orbit or a close trajectory with proto-Earth, which ultimately led it to its fateful destination. Its composition was primarily rocky, with a possible presence of metals in its core, very similar to Earth's composition. This is crucial because it helps explain the chemical similarities we observe today between the Moon and Earth. How have scientists concluded that Theia actually existed? No one has found intact remnants of Theia floating in space. The key lies in the chemical and physical clues left by its consequences. Lunar rocks, analyzed in laboratories, show an isotopic composition almost identical to that of our planet. If the Moon had formed from a completely foreign body, we would expect notable differences in these isotopes. However, the match is striking. This led researchers to seek a scenario where the Moon formed mostly from terrestrial material mixed with that of a planet-sized impactor. That impactor is what we call Theia. And why is Theia so important in the history of the solar system? Because its existence and subsequent disappearance in the collision with proto-Earth not only explain the origin of the Moon, but also fundamental aspects of our planet's evolution. Theia represents one of the many protoplanets that populated the early solar system. But its fate made it the protagonist of a unique event: the creation of our natural satellite. Understanding Theia is understanding how the chaotic and violent processes of the past were necessary to build the world as we know it today. What was our planet like before it became the blue world we know today? About 4.5 billion years ago, Earth was a sphere in construction, a proto-Earth still far from resembling the home we inhabit. Its size was already considerable, although it had not yet reached its final mass. The surface was covered by oceans of magma, and the continents, as we conceive them today, didn't even exist in nature's imagination. The environment was hostile, dominated by extreme temperatures and volcanic activity much more intense than anything we can observe today. Did an atmosphere exist at that time? Yes, but it was radically different from the current one. It was a primary atmosphere composed mainly of hydrogen and helium, the most abundant elements in the universe, but incredibly volatile under the intense solar radiation that prevailed in those early times. This primitive atmosphere was so light and sparse that it could barely be retained by the gravity of the young Earth. Constant volcanic eruptions released gases like water vapor, carbon dioxide, ammonia, and methane, creating a toxic and opaque mixture. Breathing in that environment would be impossible for any known living being. Did Earth already have liquid water? Surprisingly, the answer is no. Although water vapor was expelled from the planet's interior, the extremely high temperatures kept everything in a gaseous or molten state. The world was literally a hell: seas of lava, meteorite rains, and a sky permanently covered by clouds of dust and ash. It's like imagining a giant oven where the ingredients of life and geology were just beginning to mix. But why was the proto-Earth so chaotic? The explanation lies in the very formation of the solar system. At that time, hundreds of protoplanets and asteroids were constantly colliding, bringing in material and energy. Each impact could change the tilt, size, or composition of the young Earth. This process of accretion, although violent, was essential. Thanks to it, our planet managed to gather the necessary elements to become the fertile world we know. However, everything was about to change with the arrival of an unexpected visitor, a planetary body the size of Mars, ready to star in one of the most dramatic events in the history of the solar system. How is it possible that two worlds, each with its own orbit and destiny, ended up colliding in the vast and seemingly empty space? To understand the fatal trajectory that led Theia to collide with the proto-Earth, we must go back to a time when the solar system was a chaotic place, where young planets shared space with dozens of Mars-sized bodies, all competing for their definitive place around the Sun. Back then, the orbits were not stable, and close encounters were inevitable. Theia, a protoplanet believed to have orbited the Sun on a trajectory similar to that of the proto-Earth, moved in a slightly inclined and eccentric orbit, as if two cars were driving on the same road, but in lanes that occasionally crossed. What caused the encounter? The gravitational disturbances from giant planets like Jupiter and Saturn played a crucial role. These disturbances constantly altered the trajectories of young bodies, pushing Theia closer and closer to the orbit of the proto-Earth. Was the collision inevitable? Not necessarily. In the gravitational ballet of the primitive solar system, many bodies simply grazed each other or were expelled into interstellar space. However, in this case, the timing was perfect for disaster. Theia and the proto-Earth ended up sharing an orbital crossing point, and after millions of years of silent approaches, the climactic moment arrived. Their trajectories aligned in such a way that the collision became unavoidable. This encounter was not a simple head-on collision. Recent models suggest that Theia struck the proto-Earth at an oblique angle, which multiplied the violence of the event and facilitated the mixing of materials from both bodies. The energy released at that moment was immense, comparable to the simultaneous release of billions of atomic bombs. Thus, Theia's fatal trajectory not only forever altered the history of our planet, but also laid the groundwork for the formation of the Moon, one of the greatest enigmas and wonders of the solar system. Can the randomness of the cosmos decide the fate of entire worlds with a single move? The story of Theia and the proto-Earth suggests that it can. What happens when two worlds collide in space? About 4.5 billion years ago, the primitive Earth and a Mars-sized body called Theia were the protagonists of one of the most violent events in the history of the solar system. This crash was not merely an accidental encounter between space rocks, but an apotheotic collision capable of forever transforming both worlds. Have you ever wondered what it would be like to witness an energy release equivalent to billions of atomic bombs exploding at the same time? That was exactly what happened in that crucial moment. The speed at which Theia impacted the proto-Earth was astonishing, tens of thousands of kilometers per hour. At that speed, even a mountain would behave like a liquid at the moment of impact. The force released was so colossal that parts of the crust and mantle of both bodies vaporized in a matter of seconds, forming a cloud of molten rock and gas that enveloped the planet. What would be an unimaginable catastrophe for us was part of the natural process of planetary formation for the young solar system. How is it possible that from such absolute destruction, something as stable as the Moon could arise? The point of impact was not direct, but oblique, which added even more complexity to the dynamics of the event. This angular collision caused enormous amounts of material to be ejected into space, while the metallic cores of both planets tended to merge within the new Earth. It's as if two drops of mercury collided and joined into one, while the rest of the liquid splashed around them. The result was a rejuvenated planet, larger and with an iron-enriched core, while the expelled material began to form a ring of debris orbiting around it. To what extent was this impact decisive for the evolution of our world? The energy released altered the rotation and tilt of the Earth's axis, conditions that would be fundamental for the emergence of the seasons and climate stability millions of years later. Additionally, the immense amount of heat generated by the collision melted much of the Earth's surface, giving rise to a global ocean of magma. This fiery sea would be the perfect setting for a new stage in the history of our planet, where the expelled remnants would begin to group together, laying the foundations for the birth of our natural satellite. The impact of Theia not only changed the face of the Earth, but it was the trigger for the creation of the Moon, and with it, everything we know today. What happens when two planets collide at unimaginable speeds? The impact between Theia and the proto-Earth triggered one of the most colossal explosions in the history of the solar system. In a matter of seconds, the energy released was equivalent to millions of times the energy released by all the nuclear bombs ever created by humanity combined. The heat generated was so extreme that the surface of both planets became liquid and gaseous almost instantly. Can you imagine a rock so hot that it behaves like boiling water? That's how violent this collision was. One of the most fascinating effects was the massive vaporization of material from Earth and Theia. Not only were stones and dust ejected, huge portions of both bodies were launched into space in the form of vapor and tiny droplets of molten rock. Why does this happen? When the energy of the impact exceeds the cohesion of matter, solids turn into liquids and gases in the blink of an eye. This phenomenon is similar to what happens when a drop of water falls onto a hot pan and disappears in an instant, but taken to a planetary scale. The collision also generated shockwaves that traveled through the young Earth like tsunamis of rock and magma. These waves traveled through the planet, fragmenting the crust and mixing materials from the depths with those from the surface. How did this affect the composition of the Earth? The lighter and more volatile elements were expelled, while the heavier ones remained trapped in the core and mantle, forever altering the planet's internal structure. At the same time, a glowing cloud of debris began to surround the Earth, initiating a gravitational dance that would change the fate of the Earth-Moon system. Finally, the primitive atmosphere of the Earth was literally swept away by the violence of the event. The pressure and heat released expelled gases into space and created a sort of temporary vacuum around the planet. This means that for a brief period, the Earth was left bare, without the protection of an atmosphere, exposed to the vacuum and the intense bombardment of solar radiation. How did this cataclysm influence the future of our world? The answer is key to understanding not only the origin of the Moon, but also the conditions that made the emergence of life on Earth possible. What happens when two worlds collide with such colossal violence that it forever transforms the history of a planet? After the gigantic impact, Earth was engulfed in unimaginable chaos. In a matter of minutes, millions of tons of rocks and metals were hurled into space, as if the Earth's surface had exploded in a fiery and turbulent cloud. But where did all that expelled material go? Did it disappear into the void? Or did it have a much more spectacular destination? The answer lies in the formation of a debris disk, a kind of chaotic ring made up of vaporized rock fragments, metals, and incandescent gases. This phenomenon can be compared to what happens when a drop of water falls into a pool of oil. The energy of the impact disperses the fluid in all directions, but gravity and cohesion cause the fragments to begin to gather into a structure around the center. In our young solar system, Earth's gravity acted like a magnet, capturing much of that material in close orbit. Was the debris disk a solid ring like those of Saturn? Not exactly. In reality, it was a chaotic mix of vapor, dust, and molten rocks, spinning wildly around Earth. The temperature in this debris was so high that many materials remained in a gaseous state. However, as time went on, we're talking months, perhaps years, the disk began to cool. During this process, the denser and heavier material tended to move closer to Earth, while the lighter fragments remained in more distant orbits. How could this seemingly unstable and transient disk become something as solid as the Moon? The key lies in gravity and the collisions between fragments. Each small collision between particles helped them to clump together, forming increasingly larger bodies. It's like watching the formation of a snowball. It starts with small flakes that, when they come together, compact and grow. Gradually, in that chaotic and scorching environment, some of these clumps reached a size sufficient to attract even more material. Thus, the debris disk was the stage where, for the first time, the birth of our natural satellite took place. Who would have thought that from such violent destruction would emerge something as beautiful and constant as the Moon we know today? How is a satellite as large as the Moon formed from a catastrophic collision? This is one of the questions that has intrigued science the most. After the violent impact, a huge amount of material, composed of fragments from Earth and that mysterious body called Theia, was left orbiting around the planet. But why didn't these debris scatter into space? Gravity, like an invisible choreographer, began to act immediately, attracting and grouping the closest particles into a dense ring surrounding the young Earth. In this extreme environment, temperatures were so high that much of the material was molten or even vaporized. However, as time passed, that ring of debris began to cool slowly. This is where something fascinating happens. The smaller particles started to collide and merge, forming increasingly larger clumps. This process is called accretion, and is similar to what happens when a snowball rolls downhill and increases in size by picking up more snow. Thus, tiny pieces began to join together, first into small clumps and then into ever larger bodies. Was this process fast or slow? Surprisingly, models suggest that the Moon could have formed in just a few centuries, a blink of an eye in astronomical terms. Thousands of fragments collided, melted, and rejoined, releasing heat and energy with each encounter. Over time, most of the material from the ring concentrated into a single object, the Moon. What began as a chaotic cloud of debris transformed into a spherical satellite, thanks to the constant action of gravity and the physics of impacts. But what does the composition of the Moon tell us about its origin? Analyses of lunar rocks show that they share many chemical similarities with those of Earth, indicating that both bodies come from the same event. However, there are also subtle differences, indelible traces of that ancient cataclysm. Thus, the birth of the Moon is not just a story of destruction, but also of creation. A reminder that, in the universe, the greatest disasters can give rise to new worlds. How do we know that a colossal event like the collision with Theia left traces on our own planet? To answer this, we must closely examine the Earth's crust, that thin mantle that covers the Earth and has preserved subtle yet fundamental clues over millions of years. Scientists have discovered chemical and structural evidence that can only be explained by a planetary-scale catastrophe. For example, the surprising similarity in the composition of certain isotopes, like oxygen, between terrestrial and lunar rocks suggests that both bodies share a common origin, a direct consequence of a violent mixing of materials. But is there something more tangible that we can identify here on Earth? One of the most intriguing pieces is the existence of two mysterious deep regions beneath Africa and the Pacific, known as Large Low Shear Velocity Provinces, or LLVPs for short. These formations, detected through seismic studies, are so dense and chemically different that some scientists believe they could be remnants of Theia's mantle, buried thousands of kilometers beneath the Earth's surface. Could the Earth literally be sitting on the debris of that ancient planet? Another fascinating clue lies in the distribution of certain hydrophile elements, that is, those that prefer iron, such as iridium and platinum. The amount and pattern of these elements in the Earth's crust do not match what would be expected from a planet that formed in isolation. It's as if, after the enormous impact, the Earth received a rain of new material, altering its original composition and leaving a chemical signature that we can still detect millions of years later. And what about the geography of the planet itself? Some models suggest that the tilt of the Earth's axis and the current distribution of continents may have their origins in the imbalances caused by the collision. Even the slightly flattened shape of the Earth could be a distant echo of that impact. Thus, the geology of our world is much more than a simple accumulation of rocks and minerals. It is the diary of a violent and creative past, where each layer holds the memory of an impact that forever changed the history of our planet. What do a moon rock and an Earth rock have in common? At first glance, they may seem very different, but when scientists analyze their isotopic composition, they uncover a fascinating mystery. Isotopes are variants of the same chemical element that have a different number of neutrons. Imagine they are like different models of the same car, all with the same body, but with slightly different engines. When comparing the isotopes of oxygen, silicon, and other elements present in lunar and terrestrial rocks, the results reveal an almost astonishing similarity, much greater than expected between different celestial bodies. This coincidence raises an intriguing question. How is it possible that the Moon and Earth share such a similar isotopic signature if the Moon is thought to have formed from the remnants of a distinct object, like Theia? If the Moon had been born from a body that formed far from Earth, its isotopic proportions should be different, as is the case with meteorites from Mars or other places in the solar system. However, analyses show that lunar and terrestrial rocks are, at the isotopic level, almost twins. This suggests that the mixing of materials after the impact was so intense that both the Moon and Earth formed, largely, with the same fundamental ingredients. But what significance does this have for understanding our past? The key is that isotopic composition is like a cosmic fingerprint. If the Moon and Earth share that fingerprint, it means they are intimately related by their origin. Scientists have used sophisticated mass spectrometry techniques to measure with absolute precision the isotopes of oxygen, titanium, and other elements in lunar samples brought back by the Apollo missions. The result? Differences of less than 1 part per thousand. It's as if two random people had the exact same combination of fingerprints, something practically impossible if they did not come from the same event. This finding not only supports the giant impact hypothesis, but also challenges researchers to understand how the mixing of materials occurred to such an extent. Was the collision so violent that the elements of proto-Earth and Theia melted and redistributed almost completely? Or perhaps, did Theia and Earth form in the same region of the solar system and thus already shared a similar composition from the beginning? The questions continue, but isotopic composition remains one of the strongest and most mysterious pieces of evidence of our connection to the Moon. This enigma is the basis of many current investigations, and undoubtedly one of the keys to deciphering how worlds are born in the universe. What is the relationship between the Apollo missions and the mystery of the Moon's origin? To answer this question, it is essential to understand that before these historic journeys, humanity could only speculate about the true birth of our natural satellite. Theories abounded, but they lacked solid evidence. It was with the arrival of astronauts on the lunar surface that a direct window to the remote past of both Earth and the Moon itself was opened. When the Apollo missions returned with samples of lunar rocks, scientists found themselves faced with an invaluable treasure. For the first time, it was possible to compare, in Earth laboratories, the chemical and mineralogical composition of the Moon with that of our planet. What were the most surprising findings? The lunar rocks, incredibly, shared many isotopic similarities with terrestrial rocks, especially in elements like oxygen. This was perplexing. If the Moon had emerged from some other corner of the solar system, its chemical fingerprint would be very different. But that was not the case. Does this mean that the Moon and Earth are made, in a way, of the same raw material? Exactly. The analyses revealed that both Earth and the Moon appear to be sisters, born from the same violent event. But not everything is identical. The lunar samples are almost completely devoid of water and show a marked scarcity of volatile materials, suggesting an extremely energetic and hot origin. This fit perfectly with the giant impact hypothesis, a colossal collision that vaporized and mixed materials from both bodies, leaving behind a satellite primarily formed from the remnants of Earth and the impactor. Without the Apollo missions, the story of the lunar origin would likely be very different. The questions that arose from the analysis of these samples revolutionized the way scientists understand the formation of satellites. Why does the Moon have so little iron in its internal composition? How can the absence of water be explained? All these questions, and the answers that have been built over the decades, have their roots in those small rocks collected from the lunar surface. Thus, each Apollo mission was not only a technological achievement, but also a journey to the very origin of our planet and its inseparable companion. How is it possible to know in detail what happened over 4 billion years ago, when life on Earth didn't even exist? The answer lies in one of the most powerful tools of modern science, computer simulations. These simulations allow us to recreate, step by step, the gigantic impact that gave rise to the Moon, using the laws of physics and vast amounts of data. It's like winding back the cosmic clock and watching in slow motion the most violent events in our planet's past. Scientists have developed computational models capable of simulating planetary collisions with impressive realism. Why turn to these simulations? Because we cannot directly witness such an ancient event or replicate it in a laboratory. The simulations function as a virtual laboratory, where it's possible to vary parameters such as speed, angle of impact, the composition of the bodies and their masses to see how the results change. It's similar to trying different recipes until finding the exact combination that explains the physical and chemical characteristics of the Moon and Earth. One of the great mysteries that simulations have helped to solve is the composition of the Moon. Why do the Moon and Earth share so many similarities in their isotopic composition, yet also exhibit notable differences? By adjusting the variables in the models, scientists have discovered that only certain types of collisions with specific angles and speeds manage to reproduce the right mix of terrestrial materials and Theia. For example, if the impact had been too head-on, the Moon would have a very different composition. If it had been too oblique, perhaps our satellite wouldn't even exist. But simulations not only explain the formation of the Moon, they also allow us to explore fascinating questions. What would have happened if Theia had been smaller or larger? And what if the impact had occurred at a different stage of Earth's formation? Each new simulation offers additional pieces to the puzzle, allowing scientists to rule out alternative theories and refine the details of the Great Impact. Thus, the tireless work of computers and specialists has transformed a story that seemed impossible to know into an increasingly clear and astonishing account of the origin of our only natural satellite. In short, computer simulations are the bridge that connects theoretical physics with the tangible evidence we have today, such as lunar rocks. Thanks to them, we can get closer than ever to the exact moment when the Moon began to exist, making the distant past of our solar system a little less mysterious and much more fascinating. Is it possible that the Moon originated in another way? Although the giant impact hypothesis with Theia is the most accepted, for decades scientists have explored other theories to explain the origin of our satellite. One of the oldest alternatives is the fission hypothesis, which suggests that the Moon broke away from the Earth due to the rapid rotation of the primitive planet. According to this idea, centrifugal force would have ripped a piece of the Earth's crust, forming the Moon. However, is this really plausible? Calculations show that the Earth would have had to spin at such an extreme speed that it would have simply disintegrated before ejecting a sufficiently large fragment. Another intriguing theory is the capture theory, which proposes that the Moon formed in another region of the solar system and, after passing close to the Earth, was captured by its gravity. At first glance, this might make sense. After all, Jupiter and Saturn have captured numerous asteroids and moons throughout their history. But here, a major problem arises. If the Moon had been captured, its composition would be very different from that of the Earth, as it would have originated in different chemical environments. However, the analyzed lunar rocks show a great similarity to terrestrial ones, especially in their oxygen isotopes. Wouldn't it be strange for two bodies originating in such separate places to be so alike? The co-accretion theory has also been considered. According to this hypothesis, the Earth and the Moon formed together side by side from the same disk of dust and gas surrounding the Sun. This idea may seem appealing, as if the Earth and the Moon were twin sisters born at the same time. But the reality is that there are significant inconsistencies. For example, if both bodies had formed together, the Moon should have a much higher amount of iron, similar to that of the Earth, and yet it does not. Additionally, the orbital dynamics we observe today would be very difficult to explain with this scenario. In light of these alternatives, why does the Theia hypothesis stand out? The answer lies in the details. Only the giant impact model coherently explains the mass, chemical composition, and orbital dynamics of the Moon. Furthermore, it helps to understand why the Moon shares so many elements with the Earth, but retains unique characteristics. Despite attempts to find distinct explanations, each new piece of evidence seems to reinforce the story of a titanic collision, the traces of which remain present both on Earth and in its inseparable nocturnal companion. Why does the Moon have much less iron than the Earth? This question has puzzled scientists for decades and represents one of the most intriguing keys to understanding the true origin of our satellite. If the Moon and the Earth share a common past, shouldn't they have similar proportions of the same elements? However, when we analyze lunar rocks, we discover a fascinating detail. The Moon is surprisingly poor in iron compared to the Earth. What is the reason behind this enigma? To understand it, we must imagine the interior of the Earth as a huge cauldron in which the heavier materials, such as iron and nickel, quickly sank to the center during its formation, forming the core. This same process occurred, to varying degrees, in many planetary bodies. Now, if the moon formed from material ripped from the Earth by a colossal impact, as the giant impact hypothesis suggests, why didn't it carry away a similar amount of iron? The secret lies in the violence of the collision that gave rise to the moon. It is estimated that the impact was so intense that most of the iron contained in Theia and in the proto-Earth concentrated in the core of the resulting planet, that is, modern Earth. The material that was expelled into space, which later formed the moon, mostly came from the outer layers, rich in silicates and poor in heavy metals. It's as if, when breaking an egg and throwing it into the air, only the egg white and shell were ejected, while the yolk, much denser, remained in the container. Thus, the moon mainly inherited the lighter materials, leaving the iron behind. This peculiar absence of iron is not just a curiosity, it strongly reinforces the giant impact hypothesis. No other theory about the lunar origin can so convincingly explain why the moon lacks a large metallic core, unlike rocky planets. Moreover, if the moon had an iron core similar to that of the Earth, its magnetic field, geological activity, and even its appearance would be radically different. Therefore, the enigma of lunar iron is not just a mineralogical detail, it is a fundamental piece of the puzzle that helps us understand how a catastrophic event in the distant past sculpted both the Earth and the moon as we know them today. Why is the moon so dry? This question has puzzled scientists for decades. When we compare the moon to Earth, the difference is striking. Our planet is largely covered by oceans, rivers, and lakes, while the lunar surface is a dusty desert with no traces of liquid water. What accounts for this marked difference, if both bodies share a common origin? The key lies in the very birth of the moon, an event so violent that it forever changed the history of both worlds. When the collision occurred between the young planet and the hypothetical body called Theia, the energy released was immense, comparable to the simultaneous explosion of millions of volcanoes. This impact not only melted and vaporized large amounts of rocky material, but also expelled the lighter and more volatile elements, such as water, into space. Think of a pot of boiling water without a lid. The steam escapes quickly, and it's impossible to recover it. Similarly, the extreme heat generated by the impact caused the water present to evaporate and be lost into the vacuum of space, leaving behind heavier and more heat-resistant materials. When analyzing the lunar rocks brought back by space missions, scientists found a surprising scarcity of hydrogen and oxygen compounds, the main ingredients of water. This not only supports the idea of a violent origin, but also helps explain why the moon lacks a significant atmosphere. Without water and without a gaseous layer to protect it, the lunar surface is constantly exposed to bombardment from solar radiation and micrometeorites, further accentuating its inhospitable character. Does this mean the moon is completely dry? Not exactly. In recent years, small amounts of water have been detected in the form of ice trapped in polar craters that never receive sunlight. However, this water likely arrived long after the Great Impact, transported by comets or asteroids. Thus, the absence of water on the moon is not only a remnant of its catastrophic origin, but also a crucial clue to understanding how extreme events can determine the fate of an entire world. What would happen if the Earth's axis were not tilted? That simple question takes us to the heart of one of the most profound effects of the collision with Theia, the characteristic tilt of our planet. Today, the Earth is tilted about 23.5 degrees relative to its orbit. But where does that tilt come from? Scientists have found strong evidence that the gigantic impact with Theia was responsible for tilting the Earth's axis, forever altering our planet's relationship with the Sun. Why is this detail so important? The tilt of the axis determines the existence of the seasons. Without that tilt, we would have no summers or winters, and temperature changes throughout the year would be minimal across most of the planet. The blow from Theia acted like a colossal push, similar to when a spinning top rotates on a table and receives a small nudge that changes its orientation. Thus, The impact was not only a violent event, but also a defining occurrence that shaped the Earth's climatic dynamics. Could life have developed the same way without seasons? It's a fascinating question. Seasonal variations have been crucial for biodiversity and the adaptation of species to different environments. The resulting tilt from the impact allowed different areas of the planet to experience alternating periods of heat and cold, rain and drought. This stimulated evolution and generated a vast variety of ecosystems. In other words, the effect on the Earth's axis was a kind of cosmic roulette that favored the complexity of life as we know it. However, the tilt is not completely stable. It gently oscillates over thousands of years, a phenomenon known as precession. These oscillations, although slow, also influence climate patterns and have been linked to cycles of glaciations and warm periods. All of this has its origins in that ancient collision. The impact of Theia not only gave us the moon, but also left a permanent mark on our planet's orientation, conditioning the climate, life, and history of Earth. What would happen if the day lasted only 5 hours instead of 24? This is not a mere speculation. During the early moments of Earth, after the collision with Theia, our planet spun much faster on its axis. The violence of the impact not only launched material into space, but also transferred a huge amount of angular energy to the young Earth. As a result, the Earth's rotation period was drastically reduced, making days surprisingly short. It is fascinating to think that, in those times, dawn and dusk occurred at a dizzying pace, completely altering the dynamics of the nascent atmosphere and the first oceans. But how can this acceleration in rotation be explained? Imagine someone pushing a spinning top. The harder the push, the faster it spins. The impact of Theia worked similarly, imparting a gigantic rotational momentum to the proto-Earth. Current scientific models suggest that before the collision, Earth's rotation was much slower. Afterward, the force of the impact notably accelerated it. This increase in rotational speed had profound consequences for the planet's subsequent evolution. And what effects did this frantic pace have on primitive Earth? A shorter day means more extreme temperature cycles and rapid changes in climate patterns. The tidal forces generated by the newly formed moon, along with the accelerated rotation of Earth, began a slow but steady breaking of the Earth's spin. Over millions of years, the gravitational interaction between Earth and the moon has been slowing down our planet's rotation, gradually lengthening the duration of the day to the current 24 hours. This process, known as tidal deceleration, is a kind of cosmic dance that continues to this day. However, why doesn't Earth continue to spin as fast as it did at the beginning? The answer lies in the transfer of energy between Earth and the moon. Every time the tides rise and fall, some of the Earth's rotational energy dissipates as heat and is transferred to the lunar orbit, gradually pulling the moon away from Earth. Thus, the legacy of that cataclysmic impact continues to influence our daily lives, literally. The spin of our planet, the length of the days, and the distance of the moon are, in part, a direct legacy of that colossal encounter with Theia. How far did the moon form from Earth after the colossal impact that gave it origin? This is one of the most fascinating questions about our natural satellite. When the moon began to consolidate from the debris disk generated by the collision, it was not as far away as we see it today. Simulations and scientific models suggest that, in its early days, the moon orbited Earth at a much closer distance, possibly just a few tens of thousands of kilometers. To put it in perspective, the moon is currently about 384,000 kilometers away. But on its first journey around Earth, it would have been so close that it would have dominated the night sky, occupying a gigantic space on the horizon. Why didn't the moon stick to Earth or shoot off into space? The key lies in the delicate balance between gravity and orbital speed. The newly impacted Earth was spinning much faster on its axis, and the moon, formed from the hot molten remnants, found its orbit at a point where the gravitational pull of Earth and the centrifugal force caused by its movement balanced each other out. If it had been too close, Earth's gravity would have completely disintegrated it, forming a ring like those of Saturn. That critical limit is known as the Roche limit, and calculations indicate that the Moon formed just outside that invisible boundary, allowing the fragments to cluster together and form a single body. Over time, the Moon began to gradually drift away from Earth. How is this possible? The answer lies in tidal interaction. As the Moon orbits our planet, its gravity pulls on the oceans and creates terrestrial tides. This friction slowly slows down Earth's rotation and, as a consequence, pushes the Moon further away. Today, this process continues. The Moon is moving away at about 4 centimeters per year. If we go back billions of years, the Moon would have been so close that a day on Earth lasted only a few hours, and tidal forces were much more intense. And what would it have been like to observe the Moon in the sky during those primordial times? According to calculations, the Moon would have appeared up to 20 times larger than it does today. Had we been there to witness it, we would have seen a gigantic, bright orb dominating the celestial vault, influencing not only the tides, but also the climate and the stability of our planet's axis. This initial closeness is not just an astronomical curiosity. It also played a fundamental role in the evolution of Earth and in the development of the conditions that, later on, would allow for life. The initial distance between Earth and the Moon is, in fact, one of the most important keys to understanding the history of our planet. What happened to the Earth's atmosphere after the colossal impact with Theia? To understand it, we must first imagine the violence of a collision capable of melting rocks and vaporizing oceans. During that crucial moment, a gigantic amount of energy was released in the form of heat, enough to transform the surface of the Earth into an ocean of magma and send part of the primitive atmosphere into space. Think of an explosion so powerful that it tears the air apart and blasts it off the planet, like a bomb stripping away the top layer of an orange, exposing its burning pulp. How much of that original atmosphere survived? Scientists believe the impact eliminated a significant fraction, forever changing the composition and density of Earth's air. What was that atmosphere composed of before the collision? It is estimated that light gases like hydrogen and helium predominated, similar to those that abound today on Jupiter and Saturn. However, these elements are very difficult for a planet like Earth to retain, especially after such an extreme event. The blow from Theia would have expelled much of these gases into deep space, leaving the young Earth almost bare, with a very thin or even non-existent atmosphere for some time. This opened the door to the formation of a new atmosphere, a second chance for the planet, now composed of gases released by the intense volcanic activity that followed the impact. What effect did this process have on the planet's climate and chemistry? The new atmosphere, rich in carbon dioxide, water vapor, ammonia, and methane, acted like a thermal blanket, trapping heat and ensuring that the Earth did not cool too quickly after the catastrophe. This stage, known as the oceanic magma era, was crucial for the subsequent development of the planet. The water vapor, released in enormous quantities, not only formed dense clouds, but also set the stage for the future torrential rains that, millions of years later, would give rise to the oceans as we know them today. Without this atmospheric reset, Earth's history would have been very different. Could it be said then that the impact of Theia was necessary for the Earth's atmosphere to acquire its current characteristics? Surprisingly, yes. By eliminating the original atmosphere and facilitating the creation of a new one, the collision laid the groundwork for life millions of years later to find a suitable environment to emerge. It is a fascinating reminder of how, in chaos and destruction, the conditions for life and stability can arise. Thus, the collision not only formed the Moon, but also forever transformed the air we breathe. Have you ever stopped to think about why Earth has a relatively stable climate, allowing life as we know it? The answer lies far beyond the atmosphere or the ocean. The Moon plays a fundamental role in this delicate balance. But how can an apparently silent and distant satellite influence our planet so much? The key is in the gravitational relationship between the two bodies, a dance that has lasted billions of years and has been crucial in preventing the climatic chaos that could have dominated Earth. The tilt of the Earth's axis, currently about 23 degrees, is one of the most important factors for the existence of seasons and, therefore, a varied yet predictable climate. Without the Moon, that tilt would be extremely unstable. Planets that lack a large satellite, like Mars, experience chaotic variations in their tilt due to the gravitational disturbances from other bodies. In contrast, the Moon acts as a kind of giant stabilizer, a top that keeps the Earth's axis nearly constant. Without this influence, our planet could have wobbled unpredictably, leading to extreme and sudden climate changes. And why is that stability so important? Imagine a world where the Earth's rotation axis changes drastically every few thousand years. The polar regions could turn into deserts and then freeze again in chaotic cycles. Life, as we know it, would have faced enormous difficulties in adapting and evolving. Current ecosystems, from the Amazon rainforest to the boreal forests, depend on the regularity of the seasons. The Moon, in its silence, has been a guardian of that regularity, allowing evolution to take its course and complex life to flourish. Moreover, the lunar influence doesn't end there. Its presence has also helped to dampen the long-term oscillations of Earth's climate, known as Milankovitch cycles. These cycles, which include variations in tilt, eccentricity, and precession of the Earth's axis, influence glacial and interglacial periods. The Moon reduces the amplitude of some of these cycles, preventing Earth from falling into climatic extremes that could have hindered the emergence of civilizations. In summary, the Moon not only lights up our nights, but has also been decisive in the climatic stability that allowed life and human history. Who would have thought that this distant satellite would be so essential to our home? What are the lunar seas, and why are they named that way if they actually contain no water? This is one of the most frequently asked questions when we observe the Moon and notice those large dark spots that dot its surface. The lunar seas, or maria in Latin, are vast basaltic plains that formed billions of years ago. But how are these enigmatic landscapes related to the gigantic impact that gave rise to our natural satellite? After the colossal collision that formed the Moon, the energy released was so immense that the young lunar surface was completely reshaped. During the first few 100 million years, the Moon was subjected to a continuous bombardment of meteorites and asteroids. Many of these impacts were so intense that they opened enormous basins in the lunar crust. But here arises the question: why did these basins fill with dark material and not remain as simple craters? The answer lies within the Moon. After the original impact, the residual heat and destabilization of the lunar mantle allowed large volumes of magma to rise to the surface. Imagine a deep wound in a juicy fruit. The juice flows out and fills the gap. Thus, basaltic magma flowed into the newly formed basins, filling the gigantic craters and solidifying into extensive dark plains. Over time, these areas cooled and became what we now know as lunar seas. And why are these seas so different from the rest of the lunar surface? The regions of the seas contain fewer craters than the older areas, revealing that they are relatively young on the lunar geological scale. Furthermore, the basalts that compose them are rich in iron and magnesium, which gives them that characteristic dark tone when viewed from Earth. Interestingly, most of the lunar seas are concentrated on the visible side of the Moon, while the far side shows very few. This raises a fascinating mystery. Why is the distribution so uneven? The explanation lies in the lunar crust. The far side has a much thicker crust, which hindered magma from reaching the surface and forming seas. In contrast, the visible side, with a thinner crust, allowed magma to erupt more easily after impacts. Thus, the lunar seas not only narrate the story of a violent past, but also serve as traces of the Moon's internal dynamics and the catastrophic event that birthed it. Every time we look up at the night sky and observe those dark oceans of stone, we are contemplating the result of a cosmic ballet that forever changed our sky. What can lunar rocks tell us about the origins of our satellite and our own planet? At first glance, a lunar rock might seem like an ordinary object, but in reality, it is an authentic fossil record of the early days of the solar system. These rocks, brought to Earth by the Apollo missions, have become key pieces in deciphering the mystery of the moon's birth. But what secrets do they hide within? By meticulously analyzing them, scientists have discovered that lunar rocks share a surprisingly similar chemical and mineralogical composition to that of the Earth's crust. This is intriguing because if the moon had formed far from Earth or had been captured by our planet from another region of the solar system, we would expect to find much more marked differences. However, the oxygen isotopes and other elements present in these rocks are practically identical to those we find here on Earth. It's as if both share a common genealogical tree, an indelible mark of the impact that united them forever. Have you ever wondered why lunar rocks are so ancient? Many of them are over 4 billion years old, making them witnesses to phenomena that Earth has erased with its constant geological activity. On the lunar surface, devoid of atmosphere and water, these rocks have remained almost unaltered since the times when the solar system was a chaotic and violent place. Thus, each lunar fragment is like a time capsule, preserving information about the original composition of Proto-Earth and Theia, the mysterious body that collided with our planet. Another fascinating clue comes from the absence of certain volatile materials in lunar rocks. Why does the moon lack water and light compounds, unlike Earth? The answer lies in the very process of formation. The extreme heat generated by the impact and the subsequent accretion of the expelled debris left the moon stripped of many of these elements. This reinforces the theory that the moon was born from fire, the result of a titanic collision, and not simply from a calm accumulation of dust and gas. In short, lunar rocks are much more than mere stones collected from the surface of our satellite. They are silent witnesses to an event that forever changed the history of Earth. Thanks to their study, we have been able to reconstruct the steps of a cosmic dance that, billions of years ago, gave rise to the moon, and with it, to the conditions that would make life on our planet possible. What really happened to Theia after that monumental impact? It's a question that has fascinated scientists and curious minds alike. Did this wandering planet completely disappear, or are there traces of its existence both on our planet and on the moon? The answer, though partially hidden by billions of years of history, lies in the clues that science has managed to decipher. By analyzing the chemical and physical signatures on both bodies, researchers have discovered that Theia did not evaporate into oblivion, but instead left a deep and permanent mark. When Theia collided with the primitive Earth, the violence of the event was such that a large part of its mass integrated into our planet. It is estimated that a significant fraction of the Earth's mantle that we walk on today could actually be material from Theia. It's as if two masses of clay collided at high speed. Parts of both mixed together, resulting in a new entity, with memories of its original components. This theory has been reinforced by the discovery of isotopic anomalies in the depths of the Earth's mantle, different from those of the rest of the Earth, suggesting the presence of fragments from a distinct body. But did everything that was Theia end up absorbed by the Earth? Here arises another fascinating hypothesis. A considerable portion of Theia's remains was expelled into space after the collision, forming a ring of debris around our planet. Part of that material, along with fragments of the Earth itself, began to clump together under the force of gravity in an accretion process that eventually gave rise to the moon. Thus, when we gaze at the satellite in the night sky, we are observing the physical testimony of that vanished planet, forever mixed with Earth's history. In summary, Theia did not disappear without a trace. Its remnants live on, silently, integrated into the heart of the Earth and in the body of the moon. Every time we walk on our planet or admire the glow of the moon, We are, in a way, connecting with the vestiges of that ancient cosmic traveler. Scientific evidence suggests that Theia has transformed from being an independent world to becoming an essential part of two celestial bodies, whose stories have been irrevocably intertwined since that extraordinary day in the history of the solar system. Have you ever wondered why tides exist in Earth's oceans and what the true role of the moon is in this phenomenon? Without the moon, life on Earth would be radically different. The gravitational pull that our satellite exerts on the planet is the main reason for the tides, those constant rises and falls in sea level that occur every day. But how does this invisible and powerful mechanism really work? The key lies in gravitational force. The moon, although much smaller than Earth, is close enough for its gravity to pull the water of the oceans, forming what we might imagine as a sort of bulge of water that follows the lunar movement. Thus, when the moon is directly above a point on the planet, its pull generates a high tide in that area and, curiously, also on the opposite side of the Earth. Why in two places at once? Because while lunar gravity attracts the water towards it, the inertia produced by Earth's rotation and the movement of the Earth-Moon system pushes the water in the opposite direction, forming a second high tide. And what would happen if the moon weren't there? Without its help, the tides would be much weaker, caused almost exclusively by the sun, which, although much more massive, is at a much greater distance. Solar tides exist, but their force is less than half that of lunar tides. Without large tides, coastlines would not have been shaped in the same way, and marine life, especially in intertidal zones, would have evolved quite differently. Let's think about the first organisms that adapted to live both in water and on land. Many depended on tidal cycles to survive and evolve. Moreover, tides do not only affect the seas. Their influence reaches the Earth's crust, also generating solid tides that cause slight movements on the planet's surface. Tides have played a fundamental role in Earth's dynamics, from the oxygenation of the oceans to the regulation of climate patterns and the dispersion of vital nutrients for life. Without the moon and its tides, the history of life on Earth would undoubtedly have been very different. In short, the formation of the moon was not only an astronomical accident of colossal proportions, but also an essential condition for the development and evolution of life as we know it. Every time we observe a tide rising or falling, we are witnessing the direct effect of the existence of our satellite, a gravitational dance that has marked the pulse of the oceans and consequently the fate of life on our planet. What role has the moon played in the emergence and development of life on Earth? This question has fascinated scientists for decades, and the answer leads us to discover how fundamental our natural satellite is to the very existence of living beings as we know them. Far from being just a bright nighttime companion, the moon has been a true silent architect of the conditions that made life possible. Without its presence, the history of our planet would be radically different, perhaps even incompatible with the biological complexity we admire today. One of the most profound effects of the moon is the stabilization of Earth's rotational axis. Why does this matter? If Earth's axis were to vary chaotically, as it does with Mars, the climate would be unpredictable, and the seasons could change in extreme and sudden ways. The moon acts as a counterweight, keeping the tilt of the axis relatively constant over millions of years. This stability has allowed ecosystems to evolve under favorable and predictable conditions, ensuring that life has time to adapt and diversify. It's as if the moon were a patient mother, gently rocking the cradle of Earth with its gravity, so that the development of life doesn't suffer from jolts. The lunar influence doesn't stop there. The tides, primarily caused by the moon's gravity, have been a key driver in biological evolution. How could a simple ebb and flow of waters influence the emergence of new forms of life? Tides create intertidal zones, spaces where water and land constantly meet and transform. These changing and challenging environments were natural laboratories where the first organisms had to adapt, favoring the transition of life from sea to land. Without the tides, that evolutionary leap might not have occurred, or at least it would have been much less likely. But the relationship between the moon and life goes even further. The protection that the moon offers against cosmic impacts is a lesser-known but surprising aspect. Although the moon is not a perfect shield, it has absorbed countless impacts from asteroids and comets that would otherwise have struck Earth with devastating consequences. Imagine the lunar surface as the hull of a ship that has taken most of the hits, allowing the fragile interior, terrestrial life, to survive and thrive. Additionally, the presence of the moon helps regulate the circadian rhythm of many living beings, including plants and animals, which synchronize with lunar and solar cycles, influencing behaviors such as reproduction, migration, and flowering. In short, the moon has been much more than a mere spectator in the history of our planet. It has shaped the physical and biological environment of Earth, creating the necessary conditions for life to emerge, adapt, and evolve. Asking ourselves what life would be like without the moon is not just an exercise in imagination. It is recognizing the deep interdependence between our planet and its satellite, and valuing the delicate cosmic balance that allowed life to flourish in this corner of the universe. Is it possible for a colossal collision like the one that formed the moon to happen again in our solar system? The idea is both unsettling and fascinating. To answer this question, it is necessary to understand what the cosmic environment was like in those distant times, and how it has changed since then. Billions of years ago, the solar system was a much more chaotic place, populated by countless protoplanets and debris wandering on unstable trajectories. The odds of catastrophic encounters were high, almost as if the cosmos were playing marbles with entire worlds. However, today, the dynamics are very different. The planets have cleared most of the debris from their orbits, and large objects follow fairly stable paths. Does this mean we are completely safe from an impact of such magnitude? While the possibility is extremely low, it is not absolutely zero. There are still wandering bodies, like asteroids and comets, traveling through the solar system. But the probability that one of them has the size and precise trajectory to cause a collision as devastating as that of Theia is practically insignificant today. Now, could a planet like Earth suffer the impact of another protoplanet in the future? For something like that to happen, a large body would have to form in an unstable orbit or be ejected from another part of the solar system. This is highly unlikely, as planet formation today is a much less active process, and orbits are regulated by the gravity of existing bodies. In a way, the solar system has reached a kind of maturity where large cosmic catastrophes are becoming less frequent. Of course, the universe is an unpredictable place, and Earth's history shows that cosmic chance can surprise us. But if we compare the current situation with that turbulent past, the difference is vast. Today, the greatest threat comes from much smaller objects, like asteroids of tens of kilometers, and not from entire planets. In summary, the possibility of a planetary collision like the one that created the moon is so remote that, by human standards, we can consider ourselves fortunate to witness such a calm stage of the solar system. However, the question will always remain open. Can the calm last forever in this vast cosmic stage? Since time immemorial, the moon has been much more than just a simple natural satellite in the night sky. Why has this object fascinated humanity in so many different ways? Just looking at the history of civilizations makes it clear that the moon has held a privileged place in myths, legends, and religions. In ancient Mesopotamia, for example, the moon was represented by the god Sin, considered the ruler of time and protector of night travelers. For the Maya, the moon had a dual role. It was a source of fertility, but also a symbol of change and transformation, reflecting its cyclical phases that greatly influenced agricultural calendars and rituals. Did you know that in almost all cultures, the moon has been associated with the feminine and the cycles of life? This is no coincidence. Its monthly phases remind us of human biological rhythms, especially the female cycle, which led many societies to see the moon as a mother goddess or protector. In Greek mythology, Selene was the goddess who rode a silver chariot across the sky, while in Roman mythology, her equivalent was Luna. In Chinese culture, the Mid-Autumn Festival celebrates the full moon as a symbol of family unity and prosperity, showing how this celestial body has inspired festivities that transcend borders and centuries. But the influence of the moon goes far beyond the symbolic. Why has it played such a central role in navigation and timekeeping? Before precise clocks and calendars existed, humanity looked to the sky to organize daily life. The moon, with its precision in phase changes, became the first great universal calendar. The ancient Egyptians, for example, synchronized their agricultural activities with the lunar cycle, while in Europe, numerous megalithic monuments, such as Stonehenge, are aligned with important lunar events. Even Ramadan, one of the sacred months in Islamic tradition, begins and ends according to the observation of the moon. Could we imagine a world without the moon? Beyond the scientific, its absence would mean losing an inexhaustible source of inspiration for literature, music, and art. Poets like Federico Garcia Lorca and musicians like Debussy have dedicated entire works to the beauty and mystery of the moon. Today, the moon remains a symbol of dreams and exploration, motivating new generations to look to the sky and wonder what secrets it still holds. Thus, the moon is not only a witness to the history of humanity, but also a protagonist of our collective imagination, reminding us that, although science explains its origin, its meaning transcends the physical and touches the deepest part of being human. Is it possible that other planets have experienced gigantic impacts like the one that gave rise to the moon? The answer is yes, and in fact, astronomers believe that such collisions were common in the early days of the solar system. Each planet bears scars that tell stories of violence and transformation, and some of those tales are as astonishing as that of Earth and Theia. For example, Mercury, the planet closest to the Sun, has an unusually high density. Many scientists think this is because, at some point, a colossal impact stripped away much of its mantle, leaving its metallic core exposed, as if it were a candy bitten in half. Venus, on the other hand, is an enigma. Its rotation is extremely slow, and it spins in the opposite direction to most planets. Could this be the result of a titanic collision? One hypothesis suggests that a massive impact altered both its rotation and axial tilt, creating a planet with days that last longer than its years. Thus, Venus shows us how a single event can change the fate of an entire world, rewriting its fundamental rules. Mars also bears the marks of ancient cataclysms. Its northern hemisphere is much lower and flatter than the southern one, and experts believe this could be due to a collision with an object the size of Pluto. Such an impact would have stripped away much of the Martian crust, sculpting the strange asymmetry we observe today. Additionally, Mars's two small moons, Phobos and Deimos, could be remnants of ancient collisions or asteroids captured after violent encounters. But what about the giant planets? Uranus is perhaps the most extreme example. This planet spins almost on its side in its orbit, with an axial tilt of nearly 90 degrees. Models indicate that only a colossal impact, with a body several times the size of Earth, could explain such a radical tilt. This collision would also have contributed to the strange distribution of its moons and rings. Saturn and Jupiter, while much more massive, also show signs of having absorbed impacts in their early stages, perhaps determining the composition of their atmospheres and the number of their moons. These examples show us that large collisions are not exclusive to Earth. They are part of the natural process of planetary formation, like pieces of a gigantic cosmic puzzle that, when colliding, shape and give personality to each world. Each impact has been both an opportunity and a risk, molding landscapes, atmospheres, and even the possibility of life arising. Thus, the story of Theia and the Moon is just one page in the vast book of violent encounters that have built the solar system as we know it today. Have you ever wondered why some planets have multiple moons while others, like Earth, have only one? Natural satellites, those silent companions that orbit around planets, tell fascinating stories about the origins and dynamics of planetary systems. But how do these satellites come into being? Are they all the result of titanic collisions like the one that gave rise to the Moon? Or are there other paths in the universe to form these celestial bodies? To understand this, let's think of the moons in our solar system as a large family with diverse origins. In some cases, satellites formed alongside their planet, from the same disk of gas and dust that spun around the young Sun. This is the case for the regular satellites of Jupiter and Saturn, like Ganymede or Titan, which slowly assembled as their planets grew. However, not all satellites are born at home. Some are captured. Mars, for example, has two small moons, Phobos and Deimos, which were likely wandering asteroids caught by Martian gravity. This capture is like a planet extending its net and managing to catch visitors from the asteroid belt. But there is a third mechanism, perhaps the most spectacular: formation from a massive impact. In this scenario, a sizable body collides with a newly formed planet, ejecting materials into space. These remnants can come together under gravity to form a satellite. This is how our Moon came to be, but it is not the only possible case in the cosmos. Astronomers suspect that other bodies, like Charon, Pluto's largest moon, may also have been born from a colossal collision. In these stories, the satellite is literally a child of violence and transformation, a reminder of how chaotic the birth of worlds can be. The diversity of moons in our solar system reveals the richness of processes that shape natural satellites. Some, like those of Jupiter, follow orderly and circular orbits, while others, like Triton in Neptune, orbit in the opposite direction of the planet's rotation, indicating their captured origin. Earth's moon stands out for its relative size and influence, but also for the mystery of its origin, so different from most. Each moon is a time capsule, a witness to primordial events and the accidental or planned encounters by gravity. What do these differences tell us about the history and evolution of planets? The answer continues to expand our curiosity, showing us that, in the universe, there are many ways to have company on the journey around a star. What does the future hold for the Moon? Although it seems unchanging up there, the reality is that its story is far from written. The Moon drifts away from Earth each year, about 3 centimeters, roughly the speed at which our nails grow. This happens due to the transfer of energy between the two bodies, a kind of gravitational tug-of-war that makes our days longer and lunar nights more distant. If we could leap millions of years into the future, we would see how the days on Earth stretch and the Moon orbits farther away. Could there come a time when we lose it completely? The answer is intriguing. Although the Moon is moving away, this process is very slow, and before it could escape entirely, the Sun will have evolved. In about 5 billion years, our Sun will become a red giant, and, in that process, will likely engulf the Earth and, with it, the Moon. So, in cosmic terms, the separation between Earth and the Moon is just a temporary stage in a story that will end spectacularly along with our solar system. However, until that moment arrives, the Moon will continue to exert its influence on our planet, stabilizing its axis and regulating the tides. Could humanity intervene in the Moon's destiny? This is a question that has begun to gain traction with plans for lunar exploration and colonization. If in the future we establish permanent bases or exploit resources on the Moon, we could, in theory, minimally alter its orbit or rotation. In fact, even small modifications could accumulate over millennia. Nevertheless, the effects would be insignificant compared to the gigantic natural processes that dominate the Earth-Moon dynamics. Ultimately, the Moon will be a silent witness to the evolution of our planet for as long as it remains. Its craters and seas will continue to tell the story of ancient impacts and cosmic events long after human life has vanished. Thus, the future of the Moon is intimately linked not only to the fate of Earth, but also to that of the Sun itself. Until the very last moment, the moon will serve as a reminder of our connection to the cosmos and the colossal events that shaped our home. What if there were a time capsule capable of preserving the oldest secrets of the solar system? That capsule exists, and it's called the Moon. Although it may seem like a simple satellite at first glance, the Moon is much more than that. It is a geological and cosmic record, a natural archive that has kept the traces of the most violent and formative events of our stellar neighborhood for billions of years. While on Earth, geological processes, erosion, and tectonic activity have erased most evidence of its remote past, on the Moon, almost everything remains frozen, as if it were an untouched museum of solar history. Why has the Moon preserved these records so well? The answer lies in its stillness. Without a significant atmosphere, there is no wind or rain to wear down its craters. Without tectonic plates, its rocks are not recycled or buried. Every meteorite impact, every extinct volcano, every particle of dust that has fallen on its surface for over 4 billion years is still there, accumulating information like pages of a book that never closes. The lunar surface is, in a way, the intimate diary of the solar system, where the great bombardments, periods of calm, and the chemical transformations that accompanied the evolution of the planets are recorded. Have you ever wondered how we know when the late heavy bombardment occurred, that period when Earth and the Moon were struck by a rain of asteroids? Much of what we know comes from the traces in the lunar crust. The craters, basins, and layers of regolith allow us to reconstruct the sequence of impacts that affected all the inner planets. It's like reading the rings of a tree, except here each ring is a crater, a layer of dust, or a subtle difference in the composition of the rocks. Thanks to the samples collected during space missions, scientists can date these events accurately and compare lunar history with terrestrial history, filling in the gaps that the tumultuous dynamics of our planet have left. But the Moon doesn't just tell us about impacts. Its oldest rocks hold clues about the primitive composition of the solar system, the presence of water in its early stages, and early volcanic activity. By analyzing the Moon, we understand what the cosmic environment was like when the planets were forming. Some even consider it a natural laboratory for investigating the evolution of atmospheres and the influence of solar wind over the eons. Thus, each lunar fragment is a piece of a puzzle that helps us reconstruct not only the history of the Moon, but also that of Earth, Mars, Venus, and the other worlds that orbit the Sun. In short, the Moon is much more than a bright object in our night sky. It is the best preserved geological archive of the inner solar system. Without it, many crucial chapters of our planetary history would be lost forever. It is thanks to its silence and its stone memory that today we can peek into the deepest past of the cosmos and understand how we got here. What is the true role of the Moon in space exploration? We often think of the Moon as just a simple satellite, but in reality, it has been and continues to be a natural laboratory, a testing platform, and the closest springboard for human ambitions beyond Earth. Since the first humans looked up and set out to reach it, the Moon became the first tangible target of cosmic adventure. It was not only the destination of the Apollo missions, but also the stage where humanity demonstrated, for the first time, that it was capable of leaving its home planet and returning alive. The Moon is, in many ways, the gateway to deep space. Why continue exploring the Moon if we have already visited it? The answer lies in its strategic and scientific potential. The lunar surface is like an untouched archive of the solar system, with traces of impacts and processes that have already disappeared on Earth due to erosion and geological activity. Furthermore, its gravity, which is approximately 1/6 of Earth's, offers the opportunity to test technologies and space habitats in less extreme conditions than Mars or deep space. It's like trying to climb a mountain first on a nearby hill, before venturing to the highest and farthest peaks. The Moon also plays a crucial role as a base for future interplanetary missions. Thanks to its low gravity, launching spacecraft from its surface would require much less energy than doing so from Earth, which could facilitate the construction of fuel supply stations or even the manufacturing of components using lunar resources. Could the Moon become the gas station of the solar system? that possibility is getting closer with new plans from agencies and private companies seeking to establish permanent bases on its surface. But the relevance of the Moon doesn't end there. Its moderate distance allows for testing life support systems, radiation protection, and work routines in hostile environments, while always having the possibility of a relatively quick return in case of emergency. It is an ideal environment to learn how to live beyond Earth, practice space resource mining, and experiment with manufacturing in low-gravity conditions. Thus, the Moon is not just a destination, it is the classroom, the workshop, and the training ground of the new era of space exploration. Without the Moon, human expansion into the cosmos would be much more uncertain and dangerous. What unexpected secrets does Theia, the mysterious body that forever changed the history of our planet, hold? It may seem that after so many years of study, everything about this ancient protoplanet is already resolved. But the reality is very different. Recent research has revealed surprising data that has forced scientists to rethink how the collision actually occurred and what specific materials Theia contributed to both Earth and the Moon. What was once thought to be a simple crash between two primitive worlds is now revealed to be a much more complex and fascinating process. For example, one of the most intriguing discoveries is the presence of strange deposits deep within the Earth's mantle. By analyzing seismic waves, geologists have detected two enormous regions beneath Africa and the Pacific Ocean, composed of materials that do not entirely match the rest of the mantle. Could they be fragments of Theia itself, trapped beneath our feet for over 4 billion years? It's as if the Earth carries hidden scars inside, remnants of its ancient adversary, reminding us that our planet is, in fact, a cosmic hybrid. The chemical composition of the Moon is also fascinating. When comparing the isotopes of oxygen and titanium between Earth and the Moon, scientists expected to find notable differences, but what they found was an almost perfect similarity. This fact suggests that Theia and Proto-Earth must have formed in the same region of the solar system, sharing very similar chemistry. However, recent analyses have detected slight variations in other elements, such as tungsten and molybdenum. These small differences open the door to new questions. Was Theia really so similar to Earth? Or does its composition hold clues about the diversity of materials present in the early days of the solar system? Another unexpected surprise emerged when analyzing the proportion of volatile elements, such as sodium and potassium, in lunar samples. The results show a remarkable scarcity of these elements, suggesting that the impact was so violent that it literally vaporized much of the lighter materials, leaving behind a Moon that is drier and less volatile than many had imagined. This finding challenges old ideas about lunar formation and forces a reconsideration of the temperature and energy released in the original collision. The surprises of Theia do not end here. Recently, some computational models have revealed that the impact may have provided key ingredients for life, such as organic compounds or water, albeit in minimal amounts. Could it then be that Earth's ancient enemy was, ironically, an ally in the emergence of life? Each new clue about Theia not only changes our view of the Moon, but also transforms what we thought we knew about our own origins. Deep down, Theia remains an open enigma, a reminder of how many mysteries are yet to be uncovered in the early history of our world. For a long time, the story of Theia seemed to end with the formation of the Moon. But what if part of this ancient protoplanet still exists today, buried beneath our feet? Geologists and geophysicists have begun to gather clues, suggesting that fragments of Theia could be present in the depths of the Earth's mantle, forever altering our understanding of the internal structure of our planet. How is it possible that the remnants of a vanished world survive on Earth? The key lies in two mysterious continents, hidden beneath Africa and the Pacific, known as large low shear velocity provinces, or LLSVPs. These regions, detected through seismic waves, are gigantic concentrations of material, with properties different from the surrounding mantle. Scientists wonder, could this strange material actually be the buried legacy of Theia? Computer simulations and geochemical analyses have begun to support this hypothesis, suggesting that, after the colossal impact, enormous fragments of Theia sank and became trapped near the Earth's core, like pieces of a forgotten puzzle. Why are these structures so different from the rest of the mantle? Studies show that these areas are denser and behave uniquely when seismic waves pass through them. Imagine the Earth as a fruit, and after a brutal blow, part of the pit mixes with the pulp but never fully integrates. In this way, the fragments of Theia would have retained some of their original characteristics, enduring the intense internal processes of the planet for billions of years. The possibility that the Earth contains remnants of another world within it is not only fascinating, but also raises new questions about mantle dynamics and planetary evolution. Could these remnants have influenced volcanism, the formation of continents, or even the magnetic field? Every clue found beneath our feet reminds us that the history of the Earth is written not only on its surface, but also deep within its heart, where the echoes of that violent cosmic encounter with Theia still resonate. How is it possible that after so many years of space exploration, we are still discovering new secrets about the Moon? The answer lies in the amazing analytical techniques that scientists have recently developed. Thanks to technological advances that seemed unimaginable just a decade ago, we can now unravel hidden clues in lunar minerals, study its history with a precision that borders on the incredible, and even detect traces of elements that previously went completely unnoticed. But what tools are revolutionizing our knowledge about the satellite that lights up our nights? One of the most fascinating methods is high-resolution mass spectrometry. This technique allows for the separation and analysis of isotopes present in lunar samples with an exquisiteness comparable to that of a chef who distinguishes ingredients in a recipe just by the aroma. Thus, scientists can trace the origin of materials and reconstruct, atom by atom, the history of the Moon since its formation. Chemical signatures have even been identified that suggest the presence of components from celestial bodies like Theia, something that until recently seemed like science fiction. Another key tool is nanoscale X-ray tomography. Why is it so revolutionary? Because it allows visualization of the interior of mineral grains without destroying them, as if you had a magic magnifying glass capable of seeing through an opaque rock. This has led to the discovery of inclusions and microscopic bubbles trapped during the violent processes of lunar formation, opening a window to the extreme conditions that prevailed after the Great Impact. Additionally, ultrafast lasers now allow for three-dimensional imaging of the tiniest surfaces, revealing textures and structures invisible to traditional methods. Equally important is the analysis of trace noble gases, such as helium or neon, trapped in lunar crystals. These gases act as time capsules and can indicate, for example, whether a rock was exposed to solar wind or protected beneath the surface for millions of years. Laboratories have perfected such delicate techniques that it is now possible to measure minuscule amounts, on the order of a millionth of a gram, and still obtain valuable information about the early history of the solar system. Artificial intelligence has also entered the scene. Machine learning algorithms analyze vast volumes of data obtained from lunar missions and find patterns that escape the human eye. Sometimes, these programs have revealed unexpected correlations between the composition of certain rocks and possible cosmic events, such as meteor showers or changes in solar activity. Thus, the combination of new technologies and scientific creativity is allowing each grain of lunar dust to become a living page of the history of the cosmos, revealing secrets we never even imagined existed. How common is it for two worlds to collide and, as a result, give rise to something as extraordinary as the Moon? To understand the magnitude of Theia's impact, it is necessary to look beyond our planet and place it in the context of the formation of planetary systems throughout the universe. When planets are in their early stages of formation, gigantic collisions are not only possible, but are a fundamental part of the process. Like pieces of a giant puzzle, protoplanets and planetesimals collide repeatedly, merging or being destroyed until they shape the worlds we know today. But why do some of those impacts generate satellites like the Moon, while others simply destroy or absorb the smaller bodies? The answer lies in a delicate combination of factors: the size and speed of the objects involved, the angle of the collision, and the composition of the materials. A head-on impact can annihilate both bodies, while a two-grazing hit may barely alter them. The case of Theia and Earth was an almost miraculous midpoint, energetic enough to eject a huge amount of material into space, but not so much as to completely destroy proto-Earth. Such impacts, while rare, have been indirectly observed in other young solar systems, where telescopes have detected debris disks around stars, evidence of recent and violent collisions. Does this mean that the formation of a large satellite is a cosmic accident, or an inevitable consequence of planetary evolution? To date, the Moon is an exceptional case in the solar system. No other rocky planet has a satellite so large in proportion to its own size. This fact has led scientists to wonder if the presence of the Moon was a unique stroke of luck, or if other worlds in other corners of the galaxy have experienced similar events. Even in our solar system, major impacts have left their marks. Uranus, for example, may have been knocked over on its side by a titanic collision, and Mercury shows signs of having lost much of its crust after a devastating blow. The collision of Theia, more than a mere accident, can be seen as a natural chapter in the biography of planets. It is a reminder that violence and chaos are essential ingredients in cosmic evolution. Without these events, Earth would not have the Moon that stabilizes its axis and regulates its tides, nor would there have been a conducive environment for the emergence of life. Thus, every time we gaze at our satellite in the sky, we are witnessing the result of an ancient dance of destruction and creation, one of the many stories of transformation that continue to unfold in the farthest corners of the universe. What mysteries remain hidden on the Moon after decades of exploration and analysis? One of the greatest current challenges is to accurately unravel the composition and origin of lunar materials. Although the samples brought back by the Apollo missions and other expeditions have revealed surprising similarities to terrestrial rocks, there are still subtle differences that scientists cannot fully explain. Why, if the Moon and Earth share a violent origin, do their proportions of certain elements and minerals vary in unexpected ways? This enigma forces researchers to rethink models and search for new clues, like detectives revisiting a crime scene millions of years later. Another fascinating question is the internal structure of the Moon. Is it possible that remnants of Theia, that ancient lost planet, exist within it? Seismic studies conducted by seismometers left on the lunar surface suggest that the Moon's core is smaller and less dense than previously thought. However, the true nature of its deep layers remains a puzzle. Could fragments of Theia be hidden hundreds of kilometers beneath the lunar crust? Solving this dilemma would help reconstruct the history of the collision and better understand how materials mixed after the impact. The exact timeline of the giant impact remains a topic of debate. Did it really occur 4.5 billion years ago, or was it a somewhat later event? Determining the precise age of the collision is crucial for understanding when the Moon's orbit stabilized and how this influenced the early evolution of Earth. Radiometric dating techniques, while powerful, still face limitations due to the complexity of rocks subjected to extreme temperatures and constant exposure to space radiation. Each finding raises new questions, like pieces of a complicated puzzle that sometimes seem to not fit together. Furthermore, computer simulations, so useful for recreating the impact and lunar formation, depend on variables and hypotheses that do not always accurately reflect reality. Adjusting these models to explain all the observed data on the Moon and Earth is a monumental task. How accurate are these digital scenarios? Could we be overlooking some essential ingredient in the cosmic recipe? These challenges keep lunar research alive, reminding us that, although we have made significant progress, the Moon still holds secrets waiting to be revealed. Are we close to solving the mystery of the moon's origin? That is the big question driving scientists around the world, and the answer may lie in the upcoming space missions dedicated to our satellite. In the coming years, lunar exploration will enter a new golden age. Agencies like NASA, ESA, China, India, and private companies plan to send probes, robots, and astronauts to places never before visited. Why such insistence on returning to the moon? Because every gram of regolith, every rock, and every new piece of data could contain crucial clues about that ancient cataclysm that forever changed the history of Earth. One of the main expectations focuses on exploring the polar regions of the moon. There, in craters shrouded in perpetual shadow, deposits of materials that have remained intact since the moon's formation could be found. If we manage to bring back samples from these locations, they could reveal chemical or isotopic signatures that help us distinguish between the remnants of Theia and those of primitive Earth. Additionally, some missions plan to dig several meters into the lunar surface, searching for deeper layers that have escaped the bombardment of meteorites following the Great Impact. Will we be able to find a purer record of that event there? But research is not limited to physical missions. New remote analysis techniques, such as advanced spectroscopy from orbit and seismic studies conducted with next-generation seismometers, will allow us to map the interior of the moon and detect possible anomalies in its composition. If fragments of Theia are trapped in the lunar mantle, these tools increase the chances of identifying them. On the other hand, Earth-based laboratories are preparing to analyze future samples with unprecedented precision using instruments capable of detecting minute differences in isotope ratios. Is it possible that we will soon have an unmistakable fingerprint of Theia? Interest is also directed towards experiments that seek to simulate the Great Impact with greater realism. Supercomputers and increasingly sophisticated physical models allow us to recreate the collision between planets with astonishing detail, adjusting variables such as speed, angle, and the composition of the bodies involved. These models will help interpret the data coming from the moon and predict exactly what types of materials we should find if the giant impact hypothesis is correct. What if we discover something unexpected that forces us to rethink our entire understanding of satellite formation? In short, the upcoming missions to the moon aim not only to unravel the history of our satellite, but also to answer fundamental questions about our own origin. What secrets does the moon still hide beneath its surface? To what extent is Theia still a part of us? Expectations grow with each technological advance, and we are on the brink of a stage where we could finally decipher one of the greatest enigmas of the solar system. Is it possible that a single event forever changed the fate of our planet and humanity? The collision of Theia with Earth not only gave rise to the moon, but also transformed our world into a place suitable for complex life. Without that colossal impact, the history of Earth would be radically different. Would we have seasons? Would life as we know it have emerged? The answer remains one of science's greatest mysteries, but all signs point to this collision being the catalyst for countless vital processes. The moon, that faithful nocturnal companion, is much more than a simple sphere of rock orbiting our planet. It is a constant reminder of the chaos and violence that reigned in the primitive solar system, but also of the opportunity that arises from disaster. Who could imagine that from such absolute destruction, something so fundamental to life on Earth would be born? The stability of Earth's axis, the tides, protection from impacts, even biological evolution, are all closely linked to the presence of the moon. Like a key piece in a cosmic domino effect, a single event triggered millions of consequences. Will it ever be possible to find fragments of Theia buried deep in the Earth's mantle or on the lunar surface? Each new space mission and every advancement in technology brings us a little closer to unraveling this enigma. Lunar rocks, isotopic studies, and computer simulations are our tools to reconstruct a story that took place over 4 billion years ago. However, there are still open questions and surprises waiting to be discovered. making lunar research a field as fascinating as it is vital for understanding our origins. Thus, the collision of Theia was not only the beginning of the Moon, but also the start of a chain of events that made our existence possible. Observing the Moon is looking back in time and contemplating a fundamental chapter of our own history. The next time you look up at the sky and see its silvery light, remember, that satellite was born from chaos, but without it, Earth would be a very different planet. What other secrets does our natural satellite hold? Only the future and science will provide the answer.